Thanks a lot, Emily, for this very, very warm introduction. Thank you, the Parameter Institute. Also, thank you, CBC, IDEAS, and particularly Nala and Chris for hosting this event. It's always really great to be here, so thanks a lot. And I'll talk a little bit about the mysteries of gravity. We'll have an amazing discussion with Nala on the pursuit of gravity. But before I get there, I should start with a disclaimer that my field of research as a theoretical physicist is in that of cosmology, which, I'm sorry, for those of you who didn't know, is not to be confused with that of cosmetology. This is my Swiss slight delay in the jokes. So cosmetology is very interesting in itself, but it is the study of the universe of beauty, which some of you may be interested in. I think what's much more fascinating is actually the study of the whole universe itself, which is cosmology. Everything living in the universe since the beginning of time, if there was even such a thing, and since until the end of time. And so in exploring the mysteries of a universe, gravity is one of the phenomena that plays the most important role. And so we really need to understand gravity at a very fundamental level. And if you want to understand gravity, really appreciate gravity, you need to try to extract yourself from all other forces of nature. You need to embrace gravity and let yourself go to it entirely. And that may be quite challenging to do here on Earth, but if you imagine yourself, as we do, in outer space, maybe orbiting the Earth, then you can fall so freely that actually you don't feel anything at all, even though you are experiencing gravity. And you don't feel anything at all because every single particle, in every single atom, in every single cell of your body, and the air in your spacesuit and the spacesuit itself are actually experiencing gravity in exactly the same way. This is something very universal about gravity. In fact, your cells are not torn or pushed apart. So there's no single cell in your body that can ever smell or taste or feel or hear gravity. Gravity is the most universal phenomenon that exists. It's a remarkable property about gravity, which we call the equivalence principle, and it is this universality of gravity that pushed Einstein to understand that there must be something more fundamental about it. If gravity affects everything and everyone in exactly the same way, it can't be encoded in the objects themselves, in the masses themselves. It has to be encoded in something deeper than all of us, in something that we are all experiencing, which is space and time. Nowadays we understand, thanks to Einstein's theory of general relativity, that, for instance, the Earth curves the structure of space and time around itself, and we're all experiencing this curvature, and that's how we're experiencing the gravitational pull from the Earth. Now, the larger the mass, the larger the curvature, and the larger the gravitational pull. Now, throughout the universe, everything and everyone is connected to this space-time, and therefore experiencing this curvature of space-time and experiencing gravity. In fact, there's never such a thing as curvature at any single point. The very notion of curvature, and therefore the very notion of gravity, requires the connection of points with one another. You can think of the fabric of space-time as a patchwork of events in space and time, and gravity is a thread connecting between them. And for us, actually, I would say, here on Earth, on the surface of the Earth, I think this experience is quite tangible, because at any single point, we may have the impression that we're living in a flat patch, and for thousands of years, we thought that the Earth was flat. But actually, when we connect different points along a journey, this is where the curvature, in this instance, of the surface of the Earth emerges, unfolds. And then when you connect points along a curved surface, along a straight line. Those straight lines may look funny and curved from the outside, but that's actually just what a straight line looks like, adapting for the curvature of the reality in which we live in. And that's why, for instance, the orbit of, let's say, the moon around the Earth may seem curved, but actually the moon is just following a straight line in the curved reality, in the curved space-time of the solar system in which we live in. And when I say this, it may seem just like a cartoon picture, even a childish drawing of what gravity is like. But actually, this picture of gravity through the curvature of space-time is so profound, is so precise, that it has allowed us to predict the motion of the moon around the Earth within a millimeter precision. And just to give you an insight on how precise this is, if we wanted to do any better, we would need to account for leaves growing on the trees in the spring in one side of the hemisphere and falling down on the other side of the hemisphere and changing ever so slightly the distribution of masses around the Earth and how that affects the curvature in the solar system. This picture of gravity through the curvature of space and time is so precise that it has allowed us to predict the difference of flow in time as perceived by satellites on orbits above our head with what we're experiencing right here, right now on the ground. And this difference in the flow of time may seem very subtle, may seem very tiny and negligible, and yet it has remarkable consequences, for instance, for GPS positioning. If you registered for this event tonight, it is thanks to accounting for these very small corrections from the curvature of space-time and how we're experiencing it at different points in orbit for satellites and here. If you're listening to this through the radio, I can tell you we are accounting for those very small corrections. And so if you imagine the level of understanding of gravity we need to reach to even being able to positioning ourselves here on Earth and live the life that we are living right now on Earth, just imagine the level of precision that we need to reach in our understanding of gravity to describe the whole evolution and the whole behavior of our universe. And in fact, when we zoom into the largest possible distance scales, to the cosmological distance scales in our universe, we already have strong indications that our universe is behaving in, let's say, mysterious ways. For those of you who can see the screen, you'll see an animation zooming out of the solar system, zooming out of the galaxy, zooming out of a cluster of galaxies, over distances of billions of kilometers. It would take us just a few millions of years to get there if we were able to travel at the speed of light, which we can't, which we won't. And what we see on those huge distances is that it seems that all of the galaxies are distributed along clusters of galaxies, which looks like a little bit like filaments, embedded in halos of dark matter, and they're represented here in blue. These are just fake color. We don't see dark matter because we don't interact with dark matter. But it looks like most of the energy present in the universe is confined along the structure of masses in the universe. And if we look at how objects behave on those distances, what we would see, what cosmologists see, is that the further you look and the further objects seem to be moving away from us. And that happens in all possible directions. And that doesn't mean that there's something specific about us and about where we are and everybody wants to get away from us, which maybe, granted, that's a possibility. It simply means that actually the universe itself is expanding. What is happening is that the very structure of space is being stretched. And so anyone in the universe sees other objects moving away from them, and faster the further away they are. But if there's one thing we know about gravity, is that it is an attractive phenomenon. We are attracted by the Earth, for instance. And so if it were true that most of the energy present in the universe was under the shape, in the form of masses in galaxy clusters and dark matter, we would expect the gravitational pull from those structures to lead to a slowdown of the expansion of the universe. Maybe there could even come a point where the expansion of the universe has slowed down so much that it has come to a halt and the universe will start contracting. At least that's what we would expect if it were true that most of the energy budget in the universe was present in the structure. But over the past 25 years, cosmologists have actually seen exactly the opposite. What has been confirmed over the past 25 years is that the expansion of the universe is not slowing down, it's going faster and faster. The universe is expanding at an accelerated rate. And this is contrary to our expectation if it were true that most of the energy present in the universe was indeed localized in some structure of clusters of galaxies and filaments of dark matter. But if we were to zoom into a completely empty region of the universe, far, far away from any galaxy, from any stars, any planet, any particle, even far away from any dark matter halo, from any black hole, from anything at all, imagine how lonely you'd be there. In the middle of what we call a cosmic void, you'd be billions of light years away from anything else that you can see. And that you wouldn't be completely alone. Even in the middle of these cosmic voids, anywhere you are, even in the middle of emptiness, you still feel with some energy of what we call the vacuum. This is a quantum energy of the vacuum which fills every pocket of the universe uniformly from here on Earth to the middle of the cosmic voids. And in fact, the discovery of the Higgs boson is the proof that even empty space is filled with some energy, in this case, the energy of the Higgs field. It's a quantum energy of the Higgs field. And that energy has consequences on other particles. And if it has consequences on other particles, thanks to the equivalence principle, we would have expected it to have implications on gravity and therefore implications on the whole of the universe. And this is not per se controversial. It's almost known for about a century that we would have expected emptiness, empty space, to carry energy corresponding to the quantum fluctuations of the vacuum. Now, if we take Einstein's theory of general relativity, and we include this quantum vacuum energy, the good news is that it does lead to an accelerated expansion of the universe. The bad news, because there's always a bad news, is that the expected rate of acceleration of the universe from this quantum vacuum energy is way too fast. And is not just wrong by a factor 2, a small computational error that you can sweep under the rug. Actually, the expected rate of acceleration of the universe, thanks to the quantum vacuum energy, accounting for particles that we do know exist, for instance, the Higgs boson, is at least 28 orders of magnitude. This is the biggest discrepancy in the whole history of physics. This is the biggest discrepancy in the whole history of humanity. This would mean, if it were true, I'm a theorist, so I'm not very good with observations, but I can tell you there's one thing I know is not true. It would mean that the space between you and the person sitting next to you would be stretching so fast that it would go faster than the speed of light, and you wouldn't be able to see each other anymore. So, again, I'm a theorist, but I think that's wrong. I don't think that's happening.